All right, sometimes a thermodynamic process doesn't fall into a nice category, and what you'll get is a diagram, a PV diagram, and just have to solve a general problem. Uh, Pretty soon I'll show you another one where you actually have an enclosed diagram. We'll take a look at how to solve one like that as well. But in this case, let's say you've got 4 moles of a gas expanding from an initial volume, zero point 0.1 cubic meters, to a final volume of zero point 0.3 cubic meters, and your pressure is going to change at the same time, from 1 atmosphere basically up to 2.5 times 10 to the 5th pascals. So they want to compute the work done on the gas, the change in the internal energy of the gas, delta U, and the thermal energy Q transferred to the gas. So how would we work with our first law of thermodynamics when just given a PV diagram like this? Okay, well, the work done, remember, is always negative P delta V, but since we're changing both the pressure and the volume here at the same time, we'll have to use the area method. And so the work being the area underneath the graph, we can add A1 and A2 together. Yeah, which is 1/2 the base times H1 for the first area, and just the base here, or the change in volume, times H2, the pressure, um, for the second area. So taking a look at that and plugging in the values from this graph right here, okay, getting our information out of the problem, we get a total work then of 3.5 times 10 to the 4th joules. So really, as long as you know how to work with areas underneath the graph, that part's really not too bad. Okay, but what about getting the internal energy of the gas, delta U? The change in the internal energy is both the work plus the heat, and we don't know the heat. So we have to work with our formula 3/2 nR delta T. But the problem is, nowhere in the problem here or on the diagram here did they tell us what the initial or final temperature is. So what we're going to have to do is work with our state, PV equals nRT, our state law, one state law, and find the temperature at each condition. So doing that, and using PV equals nRT and putting in what we know from the graph or from what's stated in the problem, we can find out that the initial temperature was 301 Kelvin. Then work with our final states, our final pressure or final volume, moles stayed the same, 4 moles, and our universal gas constant R, we get a final temperature of 2,260 Kelvin when we do the algebra there. So we can take both those temperatures and everything else they've given us in the problem, the number of moles, we can subtract the two temperatures, final minus initial, and we get that the change in the internal energy of the gas had to be 9.77 times 10 to the 4th joules. So we know the work, we know the change in the internal energy. The one thing left that we can find then is the thermal energy transferred during the process. And using our first gas law, we realized that heat transfer would be the internal energy minus the work. Since we have both of those values already, we can just plug them right in. And what we find out is that we get positive 6.27 times 10 to the 4th joules, and that positive means that heat was added to the gas. And that's an example of a general problem.